so dark. Where's Jason? Not coming. So is he late or? Okay. Okay, go ahead and scan that. We'll just get started. Got that, Emma? Okay. No, no pretest. I figured, I was about to say, I want to cover calculation problems today. So at the beginning, I didn't think we have enough time to cover all of the topics, but after we go through, maybe we are a little bit ahead is what I'm trying to say. We are a little bit ahead on the topics we covered. What? Engines, right? Transmissions, drive axle, suspension, steering, braking, cooling. Well, engine cooling we did discuss in the engines. So yeah, I mean we pretty much, and some electronics, safety, power windows. I mean we pretty much cover like the surface, obviously, but because this is an introductory class. But I didn't have any calculation because I didn't think we have time. But we finished many of the topics. We are leaving. I still yet to do the battery for EVs. So we're going to get into a hybrid and electric vehicle. But before we get into that, I will spend maybe 2 weeks on some basic calculation, and I'll emphasize basic, right? Because obviously engine design and all this is more complex. But what we'll do today, I want to do air-fuel ratio mapping, fuel maps, and so AFR relates to injector and ignition map, timing map. Okay, so we'll do those two, and then if we have time, we'll do maybe a little bit of cooling capacity. Okay, so let's first talk about the AFR ratio. AFR ratio targets are typically not typically, this is the stoichiometric ratio. So stoichiometric means like that's the perfect ratio, right? That's chemically speaking, that is the ratio. And that's a mass ratio, by the way. It is a mass ratio, not a volume ratio. Now, during acceleration and during full wide open throttle, we'll aim for different ratios. Typically, you go into the 13.5 ratio and 12.5 ratio under acceleration. In turbos, usually you aim for 12. So this is kind of an acceleration ratio, and 12.5 will be like full acceleration or wide open throttle for non-turbo engines. Now, for forced induction, especially turbos, you will aim for 12 to 1. Superchargers, you can still stay here for superchargers just because the nature is a little bit different. Turbos are just hotter. Because it's hotter, the rich mixture kind of helps with the cooling down of the combustion temperature. That's what you want to maintain. If you go into a more lean, I think the most horsepower you can get is at 12.5 actually if you tune it for maximum horsepower. I think it's a bit dangerous. And dangerous meaning like if something happens to your injector, like a little bit clogging here and there, you can get to 13.5 and combustion temperature shoots up significantly. So you just want to be on the conservative side. Superchargers are more tolerant to combustion risk, so you can stay there for superchargers. Now, let's not touch that for now. Let's just stay with naturally aspirated engines. And these are the target AFRs. We're going to try to do a very basic injector calculation. Okay? So let's consider I'm going to write the problem here. This is just a sample problem. So a 4-cylinder engine. Let's do an idling situation. The MAF sensor reading is 5 grams per second. Now, the MAF itself measures voltage, hot wire anemometer, but let's skip the electronics and just say it detects 5 grams per second. So target is this for idling, okay? So target AFR is 14.7 and we are running at 900 RPM. Idling, just idling. Idling 14.7, perfect combustion. Our fuel injector size is 250 cc. And typically fuel injectors cc per minute. So this is kind of the flow rate of your fully open injector. If you just open it, 100% duty cycle, and it sprays 250 cc per minute. That's what it means. You can use the density of the fuel as 0.74 kilogram per liter. Okay? So calculate what is the required injector pulse width for this situation. So just one value in the fuel map. Okay? The fuel map is like an Excel sheet. You know, you land on one of these, right? This RPM. This is the map for pressure measurement or load, if it's a math. Okay? So we're just calculating a single value at this particular instant. So the calculation goes, first, what is the fuel mass flow rate that we need? Well, the nice thing about math, this is mass airflow sensor. It already measures the mass, literally the mass rate, not just the volume rate, the mass rate of the air coming into the engine. And so nice, right? I mean, we have 5 grams per second and we know the fuel. So we just divide 5 grams per second air divided by 14.7. That gives you, oops, too many zeros. 0.34 grams per second fuel. Right? Now, we gotta convert this into volume because our injector size is in volume. cc means centimeter cubic. So, now we need the volume or fuel, but in terms of volume flow rate. And this will be multiplied by the density, divided by the density. So we got 0.34 grams per second. And if you're confused whether you multiply or divide, then you look at the units, right? This is grams per second. I mean, 14.7 is unitless, so you just divide. You end up with the same units. But this is grams per second. Should I multiply or divide by the density to get mass? What I want here is cc, right? Or liter per seconds, or liter per second. So we have 0.74 is kilograms on the top, liters on the bottom. I want liter on top, so I want it on the bottom. So we have 0.74 kilogram for 1 liter. So that's how I do that, right? Now cc is milliliter. So therefore, if I want cc, then, and this is kilograms, right? So I have to multiply by 1,000 grams. So to make it into grams, and I have multiplied by 1,000 to make it into milliliters, right? So if I want to be proper, I'm gonna make this a bit long. Okay, so multiplied by 1,000 gram, 1 kilogram, okay, multiplied by 1,000 milliliters or cc divided by 1 liter, even though I'm just multiplying by 1, okay, nevertheless. So grams, so I end up with cc per second, right? So we have 0.459 cc per second. Okay, so basically mass rate, volume rate, that's it. Now, let's get to the injectors. At 900 RPM, how many injections we get per second? At 900 RPM, how many times does the fuel opens for a cylinder?
Divided by 4. 4.
Divided by 4. Why do we divide by 4?
Because one cycle, the injector will open one time for combustion.
One cycle, and how many stroke? Is obviously a 4-stroke engine.
4-stroke.
Yeah, I mean 4-stroke engine, right? This is revolutions, right?
Or revolution.
It's not cycle, right? What you read on the tachometer is, this is revolutions per minute. 1 revolution, how many cycles?
1
Half a cycle,
quarter.
right?
Oh,
Down,
yeah, 1 down.
up.
Yeah.
So, intake. So intake, compression, power, and exhaust. So, intake, compression, 1 revolution, power, exhaust. So you got 2 revolutions, right? So you got 2 revolutions. So basically, the injector shoots 1 time per 2 revolution, right? And we need to get that into seconds. So we're gonna do 900 revolution per minute times 1 minute, 60 seconds. So we divide. And then we get revolution per second. I need to get that into injections per second. So we got 1 injection per 2 revolution. That just helps me in determining whether I divide or multiply. So I like to write things in fractions like this. So we end up with 900 divided by 60 divided by that. So we have 30 injection per second. Right. 15. Oh, sorry, and then this is for a single cylinder, right? And then across all cylinder, so this is 15, right? 900 divided by 60, 15. So 7.5 injections per second per per second divided by the total injections. Because remember, this one, I'll just label this, right? Steps. This one is based on the entire airflow, which flows to the 4 cylinders. Or what you can do is also to divide that by 4, so you have a single cylinder calculation. But because we are doing a total mass flow and a total volumetric flow, so the total has to be divided by total for 4 cylinder. Okay? So this is for all 4 cylinder. Or you can divide it by 4, but then you just use 7.5. You know, either way, it's fine. So we have 0.459 cc per second divided by 30 injections per second. So we have 0.0153 cc per injection. Okay? Are we good so far? Still? Okay. So for every spray in each fuel's injector, we're going to inject this much. My fuel injector size, so sorry, this is not pulse width yet. This is the pulse volume per injection. Okay? That's step number 4. And finally, the pulse width. You basically open the 0.0153 cc multiplied by 251 second, no, that's minutes. 1 minute, 250 cc multiplied by 60, 250 cc per minute. And I want seconds, right? So 60 seconds per 1 minute. But I want seconds. I want the final units. So leave it. Okay? So we have 3.68 milliseconds. Okay, obviously I end up with 0.00368. So this is milliseconds. Okay, does that make sense? So first, total fuel mass flow, volume, has to do with density. And then we look at the injector shoots 1 time per 2 revolution for a single cylinder. So we have 7.5 injection per second per cylinder. We got 4 cylinders, total of 30 shoots for the entire fuel per second for all 4 cylinders. And so if we average it for 4 cylinders, then it's 0.0153 cc per second per injection. And based on our injector size, 250 cc per minute, convert that into seconds and milliseconds, you get that. So basically the fuel injector opens for only 3.68 milliseconds per injections, and it will spray this much. Looks tiny, but that's on idle. So we are talking about a very, very tiny fraction of time. Okay? Now, I want this to be an active learning, so I give you the basics and the concepts, basically. So what I want you to do is go into Gemini or kind of create a simple field map. Just a 3x3 field map. So the RPM, let's do 900, we did that. Okay. This is at idle. This is at acceleration. This is at WOT, which is wide open throttle. So 900, let's do a, what's a mid-range RPM? 3000. And let's do a 5, let's do red line. Let's do 6000. Close to the red line. Okay? Now, for idle, our target AFR is 14.7. Our acceleration is 13.5 target. And then a 12.5 AFR for WT. Now, before you use the AI, I want you to do it by yourself first. Pick one of the column, pick one of the cell values. So here we have 3.68 millisecond, right? So let's do this one. Let's do the middle one. Do it on your own. And then without AI first, so you kind of understand the steps. Okay, just follow the same step. Different target AFR, different RPM, same fuel injector obviously, and then let's see what kind of millisecond we got. Okay, go ahead and do that. And then we'll complete the fuel map with AI, so it saves time. But I want you to first understand the calculation.
The max air fuel still the same?
The max, this one?
The max air fuel, the MAF.
Oh yeah, that will be different. Why don't you estimate that for 3000 RPM using AI? So just estimate with this situation. Let's create a assumption that it's a 1.8 liter engine. Yeah, you wouldn't have the math reading, that's right. Estimate the math reading with AI. if we kind of just do a linear interpolation, it'll be 16.67, but under acceleration, it'll be a bit more.
For the math, do we take it from the idle or cruising? Or
This one accelerated.
accelerated?
So we are calculating a mild acceleration. Just do a mild acceleration.
It says around 22 to 28 grams per second.
Okay, yeah. I mean, if you scale, if you do the same idle for 3,000, then it's just a 3,000 divided by 900 multiplied by 5, right? Which is 16. But under acceleration, you'll have more. So you're using 26 grams?
Yeah.
Okay.
I mean,
Am I in the way? 26. What do we have? Almost. Not yet. Yeah. So you can mention the numbers, and I'll just revise it here. So what did you use for the grams? Math. 26. And so what do we have here?
The fuel also changes. No,
Oh yeah, sorry. 13.5.
1.926.
Okay. And what does that mean for the volume?
6, and then it comes to 2.603.
cc per second.
Yes.
Okay. This is 3,000. And so how many injections per second? Total?
For 4-cylinder total.
Yeah, 4-cylinder.
100.
100?
Yes. 100. Yeah.
Okay.
And then just divide by 100.
Total fuel would be
0.603
2.603.
divided by 100.
So we have
0.02603.
0.2603.
603.
Okay.
CC changes 0.015. 0.02603.
603.
Then it comes down to 6.24 milliseconds.
Okay. similar? What did you use for the
23.
oh 23? Okay, then it'll be different, obviously, right? But you have trouble following, or we're good? Which step is a little bit difficult for you?
I think for P.
Step 3. Okay. Well, this is basically a ratio. I mean, if you want to think of it, I mean, you rotate faster, so you get more injections per second. This times force. You forgot to multiply by 4. Okay. So we have 6.24 milliseconds. Now, I want to do one more thing, which is duty cycle. You remember what the concept of duty cycle is? What is duty cycle in general? Just in general, in engineering. What is a duty cycle? Let's say I buy a vacuum and a vacuum cleaner, right? And my duty cycle is 50%. What does that mean? My usage duty cycle is 50%. So how often and how long do I use my vacuum cleaner?
Yeah, 50%.
Which is like how many hours? What is 100% duty cycle?
So if I turn it on for 1 minute, I use it for the full 1 minute.
Uh-huh.
But if it's 50% duty cycle, I used it 30 seconds.
Right. So it can be 12 hours in a day or 30 seconds in a minute, right? So that's what duty cycle means. So the question becomes, what is the duty cycle of this injector running at this millisecond? The question is important because 100% duty cycle for an injector means you're going to spray this much all the time, right? So 100% duty cycle means your injector is open all the time. And it becomes like a hose, basically. Just spraying all the time. Now, that is not good for several reasons. I mean, one is that, we still get the stroke, right? I mean, basically you're spraying all the time in all strokes. Second, your spray becomes inconsistent when your injector is open all the time. Third, it can be stuck open because it's not designed to open all the time, right? It's designed to give pulse. So the question is, what is the duty cycle of this millisecond? How would we calculate that? Like if my injector is open 6 milliseconds for 6 milliseconds, what is the duty cycle? What do we have to do to calculate for that? Or maybe the 3.68 millisecond. It doesn't matter. Does a 6 millisecond pulse width means that my duty cycle is twice? That's a trick question. The answer is no, it's not. Why?
It's just only the duration. It's not the
Right.
times it opens and closes.
Right, so the question is, if I open the fuel injector for 6 milliseconds, how long is it closed until it's open again, right? So if I open it for 6 milliseconds, how long do I keep it closed and then open again for 6 milliseconds? So that is the question of cycle time, right? So if this is one cycle, you got 4 strokes, right? And I open for 6 milliseconds, 6.24, this is one cycle. So the question becomes, I open 6 milliseconds until I open for the next cycle, right? And this cycle happens very fast, by the way, right? So the cycle is a 4-stroke cycle, so we have 4 strokes. So along this, we have 4 strokes like that. But the injector is not opening for the entire intake stroke. It just opens enough to give the fuel that we need, right? So if we want to know the duty cycle of this period, then I need the value for this period. If this period is, say, 100 milliseconds, just to make it simple, this will be 6%, right? So the question is, what is that cycle time? How do we calculate that? Say for 3000 RPM. So 3000 revolution per minute. I'll just erase this, okay? We need a bigger whiteboard. So we have 3000 revolution per minute. And that's minutes per second. 60 seconds. Okay, so that's revolution per second. And we have how many cycles per revolution?
2 revolution, 1 cycle.
2 revolution, 1 cycle. So it's 0.5 cycle, right? Per revolution. So what we have here is cycle per second. Can you run the math? 25 cycle per second. So what is my millisecond for 1 cycle? What do you do to this number?
Times 6,000. No, 100. 100,000.
No. 25 cycle per second. So how many seconds per cycle?
How many cycles per second? We're looking for.
We're looking for seconds per cycle or milliseconds per cycle.
Milliseconds.
Yeah, but seconds per cycle first.
Oh, we just like switch it around, inverse.
Ah, yes, 1/25, right?
Yeah.
So 1/25 is
0.4. 0.04.
0.04 seconds per cycle.
Yes.
So it's 40 milliseconds per cycle. So if this number is 40, what's the duty cycle of this?
15%.
15%. Which is a realistic number for cruising. Usually, I mean, again, they keep it under 80, but for passenger cars, I mean, we're talking like maybe 50-60% at most. That's why when you boost your engine, you often need to upgrade your injector, because our injector was 250 cc. You know, you usually increase it like 50%. So you would buy something like a 330 cc. And that's what I did for my Integra when I put a turbo in it. My stock horsepower was 170, and I aimed for 250 horsepower. So you can just extrapolate it if you want, right? I mean, you need to upgrade your injector. So you keep the duty cycle about the same, the maximum duty cycle. Okay? So calculate real quick, maybe, just for an exercise. So for an idle, during idle, what are we looking at? Duty cycle percent. milliseconds per cycle, right? Which is would be different for 900 RPM.
Uh, 7.5 cycle per second.
Cycle per second, and so
By 0.13333.
0.133